We are continuing with interior point methods. Let's take just a minute to remember the basic formulation and what we've seen so far. So we are always thinking about minimizing a linear function subject to some set, and the special property that this set has is that it has a barrier function. So F0 is what we've been calling our barrier function. And its goal is always to maintain feasibility. We should always have in mind, as an example, the negative log is what maintains non-negativity. And so what we're doing is replacing this with a penalized version, minimize ft of x, which is equal to t times the original objective, c transpose x, plus f0 of x, and then we're letting t go to infinity. And we mentioned that there are three main objectives that we need to verify to make this, that map out this agenda. So first, we should be able to maximize ft quickly. Minimize. We should be able to minimize ft quickly if we start close enough to xt, which we've defined as its minimizer. And note that because f0 is strictly convex, linear plus strictly convex is strictly convex, so we have a unique minimizer. So I've written equality here. Secondly, we need and this we did last time. So we showed that if lambda f of x is less than 1/4, then we have actually we didn't show this, we mentioned. Then we have quadratic convergence. Next thing we need to do is we need to be able to increase t quickly. So I would like to update t by some constant multiple, 1 plus alpha times t. And again here, as I've mentioned a number of times before, the trade-off is exactly with the tension with the question in the first question here. If alpha is very big, then the function is going to change quite a bit. We would expect the minimizer to go far away. We're in danger of not being in this region of quadratic convergence. So this is what we need to show. And then finally, we need to show that that C transpose XT is close to C transpose X star, the optimal solution of the LP. So I need to show that this is small. And in particular, we're going to show that this is bounded by something that goes down in T. So we've essentially described the result in one. So we have a characterization that tells us that as long as this Newton decrement, which we defined last time, remember this is the part about the local norm, is less than 1/4, then we're guaranteed to have quadratic convergence. So what are we? So what we're going to do is, again, just to highlight the main points that I made in the previous slide, is that we have some t0. I'm going to pick, and then each time I'm going to update according to 1 plus alpha times the previous t. So typically we'll initialize this at 0. Or close to 0. So if we did it at 0, of course, this multiplication would not be very productive. And so what we need is to make sure that lambda ft of ft plus of xt is less than 1/4. This is the main, where again t plus is as above. So this is what we want to do. So let's dig into this a little bit more. So we've got so again, I need my lambda of ft plus of xt is less than 1/4, and just recall again that xt is equal to the argmin of ft of x, which is equal to t times c transpose x plus f0 of x. And also recall our definition of the Newton decrement. So this is the dual of the local norm. And so recall that lambda f of x is defined as the gradient of f evaluated at the point x, measured in the dual of the local norm, again at x. So you can see the previous session to see the definition of this. And the fact that we're using this local norm, use of this local norm, is really critical for us. So I want to show you through an example why that's the case. But let's see what this what this norm is. So for us, we have lambda of ft plus of xt. This is what we want to evaluate. And again, just plugging into the definition above, this is equal to the norm of gradient of ft plus of xt, and it's the local norm evaluated at the argument of the gradient. So that is xt, and of course the dual norm, because we're talking about gradients. Okay, so let's plug in because the relationship with respect to t is actually pretty simple. Remember, t only appears in the linear function. So actually, we can simplify this considerably. So this here is equal to, let's write out let's use what ft is. So this is ft. So in particular, if I have any two t's, ft1 and ft2, their difference is just in the linear term. So this is something important that we're going to use. So my point here is that ft1 for any t1 of x is equal to t1 minus t2 times c transpose x plus ft2 of x. So they're all related like that. After all, ft is just t times c prime x plus f0. Okay, so this is so we're going to use this, and in particular, this means that the gradient is with respect to t. Now, what's the only thing that survives? This is not an argument here, so we're not going to take we don't take the gradient with respect to this argument. It's only there's only a t in the linear term. So that means if I take the gradient here, what is it that we get? This is just equal to t sorry, I'm taking the gradient with respect to x, not with respect to t. So if I take the gradient with respect to x, what is this equal to? It's equal to t times c. Linear term in x, only t times c is left. Whoops, sorry. Plus the gradient of f0 evaluated at xt. Okay, so this this is suggestive, but it doesn't help me very much. But notice what I can do here very easily. This is also equal to the gradient of t plus minus t. I'm sorry, this is t plus here. This is t plus. So it's also equal to the gradient of t plus minus t times c. I subtracted out a tc, so now I'm going to put it back, plus tc plus the gradient of f0 at xt. But what is this? This is exactly equal to the gradient of ft at xt. And if you note this definition of xt, it's the argmin of a convex function, unconstrained, and therefore that means that this is equal to 0. So that goes away. So that simplifies my expression of lambda ft plus evaluated at xt. It's just equal to t plus minus t times c. Or just, since all norms are positively homogeneous, I just take out this term, t plus minus t times the norm of. Okay, so let's think about what this gives us. So if let's take it one more step. So this is equal to, if t plus is 1 plus alpha times t, this is equal to alpha times t times c xt star. And what are we asking for? We're asking for this to be less than a quarter. This is what we need. But how could this possibly be less than a quarter? C is just a constant, and I'm multiplying by c here. So you see why I said that use of the local norm is critical, because there's no possible way that if I replace this norm with something that's not changing, that doesn't depend on t itself, that I could ever hope to have this work. So remember, we need this to be less than a quarter. So immediately we need that this local norm better be behaving like something proportional to 1 over t. Okay, so the local norm is absolutely critical. So let's look at I guess so this is the main, let me put the summary here. So the summary is that we need this to be something like 1 over t. And the constants are constants. I mean, the 1/4, all of these things, remember, even the definition of self-concordance had that 2 in it. So those constants are just to make the analysis come out clean. The main quantitative requirement that we have is this. So let's even see why, why do we expect that something like this would be true? Let's remind ourselves what this local norm is. Again, this is a dual norm. So that means that C star of xt, just going to write out the definition of the dual norm and remind us that the local norm is this quadratic norm using the Hessian of f0 at xt. So this is equal to the supremum, just by definition, of h in the local norm, not the dual norm, of h transpose c, which is equal to the supremum of h transpose, I'm just writing out the definition of the dual norm here, times the Hessian of f0. And again, just a side comment, remember that all the ft's only differ in the linear term, c transpose x. And so all their Hessians are the same. That's why I'm always writing, the dual norm is always computed with respect to the Hessian of f0, or equivalent to that. But what's changing is the point where I'm evaluating the dual norm. In other words, the point where the local norm, the point where I'm evaluating this Hessian. So the quadratic itself changes. So it's this evaluated at xt. It's the supremum over all of these h's of h transpose c. And just check for yourselves if you haven't done this exercise before. Useful, check as an exercise that the dual norm brings out the inverse of the quadratic. So the dual norm of a Euclidean-like norm, of a norm in this Euclidean family, which isn't, so again, it's the Euclidean norm if I replace this matrix with the identity, is equal to C transpose times this inverse times C. So this is the dual norm. So intuitively, what is it that we're expecting, or why is it reasonable that that this is going to have the right property? So remember that f is a boundary function, which means it's ramping up to infinity near the boundary. And the only way something can go to infinity in a finite amount of time is if it's sloping more and more and more. So if it's getting increasingly curved, which is exactly what minus log x does near x equal to 0. And we're actually going to do that computation just as a check on the next slide. But that's why we should expect, or it's at least not unexpected that this is going to be that this is going to be something quite small. So in other words, because the largest eigenvalue of the Hessian, we expect it to be growing. That means that it will, because the curvature is growing, the inverse is going to be something that shrinks. So this will be small. Okay, so let's actually see this, see the calculation. But the intuition is that this is somehow small as xt goes to the boundary, which is what we want. Okay, so let's do an example. Very simple example, linear program that we could all solve. I want to minimize a scalar C transpose x, C is, or just C times x, subject to x greater than or equal to 0. Now, let's at least carry through the agenda for this simple setting where we can actually, we don't have to resort to Newton's method. We actually can calculate ft at every time. So So what do we have? So we've got ft of x is equal to t times, again, no transpose even needed, cx minus log x. This is our barrier function. So f0 of x is equal to minus log x, and therefore we can compute its first derivative and second derivative. The first derivative of ft of x is equal to t times c minus 1 over x, and its Hessian, or just its second derivative, is again going to be the Hessian of f0, which is just 1 over x squared. Non-negative, it's convex. So now let's compute what our optimal solution is, xt. Xt is by definition equal to the argument of t times c transpose x minus log x. I just take the derivative, set it equal to 0. So looking upstairs, I've got, so take derivative, set equal to 0. I've got tc minus 1 over x equals 0, or x is equal to 1 over t times c. This is my solution, solution xt. Okay, so now let's compute the dual norm. What is c, the dual norm at xt? So this is, again, that same calculation that we had before, but it's a little bit easier in this case. It's a supremum of c times h, subject to h in this local norm, not the dual norm, less than or equal to 1. We did this calculation before. So what is, so this is equal to, again, I think it's pretty straightforward, but it's worth seeing all the details. So what is this? I need to look back at what my second derivative is. It's 1 over x squared. So this is equal to, I can square these equivalently just to spare myself the trouble of dealing with square roots. So this is the same as h squared over xt squared being less than 1. Or in other words, the most I can make h squared is xt. I can make a, so this is equal to, it's the absolute value of c times xt. And now we can look over and see what xt is. So indeed, this is exactly equal to 1 over t. Okay, so this is what we wanted. So let's go back to the previous page where we had done our calculation of what this implies. Okay, so let's flip back to what we had. Where are we? So I need, in order to have this, what do I need to compute? I need to compute, I have that lambda of ft plus at xt is just equal to my alpha, which I'm hoping is positive, times t, times this norm of, the dual norm of c, dual local norm of c, and we want that to be less than 1/4. And what we just did now is for the very simple example of log, we did this calculation. So we did this calculation. So that means that we can take t plus equal to t plus 1 over 4 times cxt star. So why is that? So why can we do that? And then plugging in what the norm of c is. This gives us t plus 1/4 times 1 over t, which is exactly equal to 1 plus 1 over 4 times t. This is our alpha from before. So the whole goal was to show that we wanted lambda of ft plus just looking back to show you again how we got here. So we wanted lambda of ft plus of xt, oops, here we go, to be less than 1/4. And we computed that lambda of ft plus of xt is equal to alpha times t times c of xt. And we just saw that we could take alpha equal to 1/4. So maybe I did these things in a little bit of a backwards. I should have done this first. So we wanted, we needed this to be less than 1/4, but we showed that this is equal to alpha times t times c norm of c, and this in turn is equal to 1 over t, so this was alpha. So therefore we could take alpha equals 1/4, and that gives us this kind of update. So let's see this again, but a little bit, but in general. And so let's do this example in a bit of a general setting, and see how it works. See how it works out, and then we're going to see that we're going to need an additional condition in order to guarantee that we have what we want in the general setting. It's an additional condition that log satisfies. Okay, so again, where are we? We want so what do we have so far? Our recap is that we need lambda ft plus of xt to be less than 1/4. And we have seen that lambda of ft plus of xt is exactly equal to t plus minus t times c of xt. And in order for this to be less than 1/4, we get that calculation that we saw on the previous page. So we get that to satisfy this, we can take t plus as large as what we saw for log. T plus equals, and I'm basically just setting this equal and solving it. T plus equal to t plus 1 over 4 times c xt star. So so this is what I need to satisfy this. So let's look a little bit more carefully at what this dual local norm of C is, not in the general case of log. Let's remind ourselves what that is. So remember that, so using the fact that the gradient of ft at xt equals 0, but also remembering that ft is just t times c prime x plus gradient of plus f0, then this is itself just equal to t times c plus the gradient of f0 at xt. And therefore, c, I can solve for c as a function of t and xt. So c is equal to minus 1 over t times the gradient of f0 at xt. So notice what I've done. C is a constant, but for every t, the property of xt and the property of the trajectory that xt takes allows me to write it in this way. So using this property, now let's see what is this norm. Is again just the norm by positive homogeneity. I can take out 1 over t. So this is equal to 1 over t times the norm of f0 of xt, again, the dual local norm. And what is it that I need? So we mentioned on the previous slides that we need this norm to go down like 1 over t. I need this to go down like 1 over t. And since I have a 1 over t sitting right here, that means that I therefore am hoping, or what we really need is for this for this to be order 1. So again, just to recap, for this to scale like 1 over t, we therefore need this local norm to be a constant. Again, we can think about why it's so important that we have that we're using this local norm. We said that the gradient of the barrier function has to be going to infinity because the function is getting more and more and more steep as we go to 0. And in fact, for log, for example, it's 1 over x. So so indeed, it's the absolute value of it. So indeed, the gradient of minus log x is going to infinity. So we could never hope to have this kind of property, but it's critically something to do with the local norm. Okay? But so my point is that as we just saw, f0 of x equals minus sum of log of bi minus ai transpose x satisfies this. We saw this for log. But for a more general condition, if we want to go beyond just log, and then we need to see what when is this satisfied more generally. So writing out what this property is, and if you go back to the exercise that derived what the dual norm is, I asked you to do this a couple slides back. Remember that this is exactly, put a recall here, this norm is equal to equal to the gradient of f0 of xt transpose times the Hessian inverse times the gradient of f0 of xt, and all of this is under the square root. Writing is a little small, but hopefully you can make it out or zoom in. So at this point we just need to put this as a condition. So, because this is what we need, and we've gotten to the point where there's not that we're not going to derive this from something else. We've exhausted our use of properties of F0, and so I'm just going to ask or try to search for a condition that basically is going to tell me that that this thing is controlled, that it's order 1. And this is so we will essentially add a condition that guarantees this. So we've reduced it to the critical thing that we need. And this is so what the key definition is. We've talked about self-concordant functions. The next definition is of a self-concordant barrier. So a function that already is self-concordant. So an M self-concordant function F is an addition called a new self-concordant barrier if its Hessian has enough curvature. Specifically, if it has enough curvature with respect to its gradient. So the Hessian of F at X is at least 1 over nu times the gradient outer product with itself. And we'll do this calculation, but you can basically see that this is essentially just a restating of the property that we need from the previous slide. So let me flip back to one slide, and you can see that in order for what we're basically asking for is for this to be small. And what does this look like? What is the biggest that this could be? So the biggest that this could be is if what happens. Remember that, think about our eigendecompositions. Everything here, the Hessians are symmetric. So I can think about their eigendecomposition. So the biggest that this could be is when this gradient happens to be aligned with the largest eigenvalue of the inverse Hessian. The largest eigenvalue of the inverse Hessian, eigenvector, excuse me, corresponds to the smallest eigenvector of the Hessian. So this thing is big whenever that is aligned, and this is exactly saying that the smallest. What is this saying? It's saying that the smallest eigenvector of that the gradient in the direction of that the eigenvector of the Hessian in the direction of the gradient is going to be at least 1 over nu, which means that in the inverse this relationship is going to be at most nu. So it's going to exactly give us this order 1 constant control of that dual norm quantity. So again, it's saying that in the critical direction of the gradient, which is where we're measuring it, the Hessian has a lot of curvature, which means that the inverse Hessian is not going to have more than nu curvature. We can just do this. We can just do this calculation. So if we have this property, I'll just write it out again, that this is dominates in the semi-definite ordering, the outer product of the gradient, then this calculation, oops, we said that this is equal to the supremum of gradient of f of x transpose h subject to the dual norm of h squared less than 1. That's h transpose times the dual norm, sorry, times the Hessian h less than 1. But I can always replace, if I replace this with something smaller, it'll allow h to be bigger, and therefore I can do that. And so this is upper bounded by supremum of gradient of f of x transpose h. H transpose, I'm going to replace this semi-definite matrix here with a smaller semi-definite matrix. Which one? Well, the one that's sitting right here. So this becomes H transpose, this rank 1 matrix, gradient f of x, gradient f of x transpose is less than or equal to not 1, but nu, because I multiplied through by nu. And so you can see what this the supremum is going to exactly equal square root of nu. So this is the calculation that that we want. So this puts all the details together. It's the next obvious question that we need to ask is, well, okay, so log satisfies this because we actually did the calculation ourselves, and now we have a general condition, which essentially seems like to be what we need. But do other things satisfy it, or is there perhaps an easier way to check? So I'll just so here's a lemma which gives a sufficient condition for a function to satisfy this property. In other words, a sufficient condition for a function to be a self-concordant barrier. The lemma says that if a function g of x has this particular log concavity property, so if g of x is equal to e to the 1 over nu f of x, if this is concave, so in other words, if f has this log concavity property, then the Hessian of f has the required property. Lower bounded in the semi-definite ordering by 1 over nu times the gradient of f0 gradient of f0 transpose. So this makes it easier to check that something like minus log x or minus log det x, they are both self-concordant barriers. So let's put this all together and see what we have. So what did we have? T plus. We said that we could take this as large as t plus 1 over 4 times the dual local norm. We also computed that this dual local norm is equal to 1 over t times the norm of f0. This didn't require any assumptions yet. It was just by definitions of xt and f0 of xt and so on. And then if f0 happens to be a new self-concordant barrier, so if f0 is a new self-concordant barrier, then we saw that the gradient of f0 xt, in other words, the gradient of c, is bounded above by square root of nu. This is a calculation we did on the previous slide. And so this tells me that t plus is equal to 1 plus 1 over 4 square root of nu times t. For log, nu was equal to 1. So we just had 1 plus a quarter times t. And you'll notice that in here, there's no dependence on x, there's no dependence on t. So that means that I can increase t at a linear rate, which is exactly what we've wanted. We can increase t at a geometric rate. And finally, step 3, and the final thing that we really need is to check, do we have fast convergence to the optimal solution? So I'll just state this as I'll just leave it as a fact for now, that C transpose X star, not X star, excuse me, XT, remember XT is the solution to FT, compared to C transpose X star, LP, this is the solution to the LP. This is bounded above by basically 1 over t, actually nu over t. And since t increases at a linear rate, this means, again, let's not confuse this with an iteration counter. Since this increases with a linear rate, this tells us that we need log 1 over epsilon iterations for an epsilon suboptimal solution. So this pretty much spells out the main outlines of the agenda for interior point method. There are several details left. I'm not going to go over all of them, but one important question is, how do we initialize this method? And so our picture here for LP we have some feasible set. So what we need to do is initialize. We somehow need to get onto the central path. So if this is my optimal solution to the LP, the path that we take looks something like that. This is called the central path. And what this means is, xt is equal to the argmin of ft. So we need to get onto this central path. And so there's one cute idea which helps us do this. And all we need is a feasible point. We can get to the central path using any feasible point y in X. And we do this as follows. So we note that if you're given y, then y itself is on the central path of a different problem. So y, feasible point of X, means that y is an element of the argmin of minus t times the gradient of f0 at y. This is a vector. Let me write the transpose a little bit more carefully so you can see what I'm writing here. Transpose times x plus f0 of x at t equals 1. You just see, just take the derivative at t equals 1, and I get minus the gradient of f0 plus the gradient of f0 equals 0, and therefore y is indeed an element of the argmin. So that means that replacing c with gradient of f0 at y tells me that I can find I have found a point on the central path of a different problem. So what do? We want to eliminate this dependence on y because we want to get back to c. So what is this point here? This point at what's sometimes called the analytic center is x0, the argmin of f0. And what is f0? It has no dependence on c. It's just equal to f0. So we can follow essentially exactly this outline that we did, but instead of increasing t, which solves our linear program, we're going to decrease it, and again decrease it at a geometric rate. So instead of increasing t, we decrease from 1 to 0, again, at a geometric rate. So the picture is that, we start, I'll pick a different color, we start somewhere else, any feasible point, we look at the gradient of f0 at that point. Who knows where it points? Maybe it points to the same solution x star, maybe it points to another one, it doesn't matter to us. Maybe it points to this solution. And this point that we found, this point here, is on the central path to this optimal solution, but we don't follow it in this direction, we follow it backwards. And the key point is that we've just used this trick to guarantee that we found something that's actually on the central path. And instead we follow it backwards and we get very close to the analytic center. So this is the story of interior point methods and basically how we use Newton's method to solve them. And it is again one of the main implementations for large-scale linear programming. Simplex is another, but interior point method is something that is used very much, exactly because it's so fast. You can specialize it beyond what we've said because we don't have to implement generic Newton's method, since we know that we just are dealing with very specific barrier functions. So there are various improvements to the implementation that I've mentioned, but this is the key idea, and this is the notion of the central path. And then for other conic optimization problems like semi-definite optimization, it is the method of choice for solving it. And in general, what it tells us is that if we have a feasible set that's given by, and we can find a self-concordant barrier function to our convex set, then we can optimize something in polynomial time. So it's a very powerful idea. So that concludes what we have to say for interior point methods.